by Gordon Jackson, and he will talk about the chapters 8 and 9, construction and installation. I would ask Gordon, please, you can now share your screen and you can start your presentation. Thank you.
Thanks, David. Hello, everyone. I'm Gordon Jackson. I'm a structural engineer and more recently a naval architect. I'm going to run through chapters 8 and 9 of the SFTB guidelines. I've previously contributed to some of those other publications that Torola mentioned at during the introduction phase. So I've got a long history in offshore concrete. So the construction process is it's really a combination of established technologies. So the methods of constructing immersed tube tunnels are very relevant, as are the construction methods for offshore platforms that have been used for the likes of oil and gas developments. But there's also an important component in you've got to connect the SFTB to a mooring and anchoring system to keep it in place, and that has an important bearing, particularly on the installation, which I'll come to later. Just to give an idea of the sort of sizes and components involved in the construction. So the SFTB, it could be in concrete, it could be in steel, or it could be a hybrid, which would be a steel shell, which is filled with concrete. But as we're with FIB here, we're primarily concentrating on concrete, and I would say it is the most likely choice for construction material. The SFTB units, they're quite large. So each unit, which might be 200 meters long, that you construct, could displace the order of 50 to 80,000 tons, and it's quite heavily post-tensioned reinforced concrete. So typically there's quite a lot of reinforcement in these offshore structures compared to civil engineering applications, and that has to be accounted for in the speed at which you can build these units, and also the complexity of fixing and detailing reinforcement. In terms of a cycle time for constructing these, I think around about 3 to 4 months per unit would be a reasonable time frame. So you've got to look at how long your crossing is, how many units would form the crossing, and then decide how many production lines you would need to fulfill a reasonable contract construction duration. You may also use pontoons with the solution. You can either, as you'll have heard, you can either support the SFTBs with tethers using positive upward buoyancy, or you can have buoyancy units in the form of pontoons, which the SFTB is suspended from. And those pontoon units, if you adopt them, they can be quite large as well, the order of 10,000 tons displacement. And again, there's a choice of materials there. They could be in steel or concrete. It probably depends upon the local supply chain in the region where the SFTB is being constructed, but steel may prove favourable for pontoons. Then if you're using tethers, these are very high tensile steel tubular elements, which could be up to 1,200 meters long when completed. The alternative is to have a mooring system in a spread mooring system, which can incorporate chain, wire rope, or synthetic ropes, such as the product Dyneema, which is high modulus polyethylene. Then there are a number of foundations and anchors, and given that, particularly if you're using tethers, there's a significant buoyancy load to contend with. The foundations and anchors can be a significant project in its own right. Then obviously you've got to connect the SFTB to shore, but I'm not going to cover that here. There are various techniques for doing transition structures which can be adopted. Just to give an idea of a pontoon arrangement, the sort of size of these units are sort of 27 by, as shown here, by about 60 meters wide. This one's in concrete, as proposed, I think, for Sognefjorden on the E39. So moving to construction, there's probably two principal ways of going about the construction process, and one of them takes its inspiration really from the method, or one of the methods that is used for immersed tube tunnel construction, where you have a construction area which could be enclosed, or it could be in the open air, where you're building your units, and then you have a two-stage process for getting the units into the water. So you can bring your units through a movable gate, and then you have an impounding basin, which can then be flooded to allow the units to float up, and then you can take them into the deeper section. You can then drain out the water down to lower level and exit through a floating gate. So that's one means of constructing, and I've got some illustrations of how that's applied from the Fehmarn project, which is I guess just getting underway. Fehmarn's immersed tube tunnel, which connects Denmark and Germany, and it's about 18 kilometers long. So in the context of SFTBs, it's probably, there's more construction work in the Fehmarn immersed tube tunnels than there would be in a SFTB crossing. So Fehmarn is arranged with in construction of the units indoors. So you can have a mechanized construction process with formwork which is bespoke to the system, and you can utilize things like overhead gantry cranes to service the construction work, and it's obviously a more productive place to construct things internally. This is another view. Here you can see the concrete being placed from booms running along the side of the construction hall, and you can see the overall shape of the immersed tube tunnel being formed. And another view later on the stage where you're building the roof top section to the unit. Now, an important aspect of these immersed tubes and also SFTBs is they have to float, and obviously they're going to form a complete tunnel in the end. So you need an end closure, which will be watertight. So you need a diaphragm type structure, usually done in steel, to close off the ends of each unit during the temporary phase. And the arrangement at Fehmarn is that it's built at grade, but you can flood you can pump water into this area here to allow the units to float up. So they're skidded out from the construction hall into the outer area, and then there's a section to this level that you can flood up to allow you to float the units from back here. You can then bring them forward, release the water from the impounding basin, so they're then afloat on their own at some natural sea level. Then you open up the gate, which can allow you to float out the units, and then with immersed tube tunnels, you have this unit to suspend them from to install them. So there's a buoyancy and lowering winch construction, which I'll get onto when we look at the installation process. And finally, you're ready to tow away off to your final site. You can see here at Fairman, they've got 6 production lines to deliver that 18 kilometers of crossing. The alternative is to use a dry dock, and I guess this is for smaller crossings where it's you're able to deal with the fact that you need to open up your dry dock to remove the units and to tow them out, and that doesn't, that's less suitable for a serial production process. If you then have to close up your dock, again, you're into a batch production process. It probably takes you longer to deliver the units overall, but it is certainly a method that can be considered for SFTBs and the pontoon units if you're constructing those in concrete. So that's the construction process. I'll now go on to the installation side. So the key thing with installation is just the sheer scale of the operations that are having to be done in what can be quite an exposed environment offshore. Most of the installation work that's been done for offshore platforms, it's a one-off operation. You're installing one piece of construction, and it's usually done in a short period of time. Here we're looking at probably constructing and installing over water over several months, or possibly through 2 seasons. You may need to stop work during winter months, possibly, and restart the following year, depending on the environmental conditions in the installation site. So there's really a lot more emphasis on getting good data to do planning of the marine operations, and there's a lot more logistics involved in terms of planning how you're going to bring all the units together, where you're bringing them from, are you going to assemble them inshore, are you going to assemble them out in the final site. There's an awful lot more to be considered. And then on the installation works, there's the structure itself, and then there's a significant piece of work in the mooring and anchoring system that has to precede bringing along the structure to attach it to. And there are quite a number of temporary structures associated with installation. You may need auxiliary buoyancy or some form of lowering platform or winch device that's providing temporary buoyancy, and they all need to be suitably designed for the environment and robust enough to do the job. But I can't emphasize more. All this is needs to be done in a healthy and safe manner. Health and safety is paramount on this work. you're potentially exposing the workforce in an island site where they could be working in the middle of the waterway. So all the workers have to come to that site each day, and they have to safely work, possibly below water, if you're doing joining operations below water, and you know, everyone needs to return safe at the end of the day. So it's a huge consideration, I think, in planning the installation. So we want to install some anchors, and there are a whole possible range of anchors from a simple deadweight to some form of pile, to a conventional drag type anchor, to a suction pile or caisson, to this is a torpedo pile. I think we're unlikely to see those on SFTBs, and there's a vertical load anchor where the plate can dig into deep soil and then give you more uplift resistance than you typically get from a drag anchor like number 3 here. And for those of you that are not familiar, this is a suction bucket or suction pile. Here's one being deployed for an offshore wind farm. It's an open-ended steel can which you suck into the seabed. So you suck it into full depth, and they're good for dealing with quite high lateral loads from mooring lines. So they're quite good for things like a taut mooring system or a semi-taut mooring system, where the vertical load is not too high, but there's quite a large horizontal load. Looking at anchors drilled into rock, if you're using a tether, then there's a very high load in those tethers, which needs to be reacted into the seabed. And if you start looking at things like gravity bases to resist that tension, they become very large. So options, if you've got a rocky seabed where you can use techniques similar to constructing wells for offshore oil and gas exploration, where you have a series of, you drill a hole, and you put in a series of casings which you then grout up, and finally you put your connection through to your tether in, and everything's sort of grouted in stages, and you've got the shear transfer on each interface to get it to the stage where the rock grout interface can carry that high tension load. And again, if you've got a rocky seabed, then you have to think about how I'm actually going to drill that that hole to put in the tether foundation. And you know, there's various solutions been proposed for dealing with uneven seabeds, where you put a template down that can give you that guide system, so that you can drill vertically into rock. So I mentioned previously that there's various stability concepts, I think, for and mooring concepts for SFTBs. It could be tethers straight to the seabed. You could use a system of tethers and anchors, or you could just use anchors. And under lateral load, in the central one here, the displayed anchors take the lateral loads or provide the lateral restraint, whereas with a vertical tether, it's the displacement of the system away from vertical gives you a restoring force to bring it back to vertical. You can, on some shorter crossings, have an arched solution, which is self-stable laterally, and then you only need to restrain it vertically with something like a tether system. So looking at mooring systems that you might employ, the types of system that are adopted range from a catenary, which is, I guess, a traditional sort of oil and gas technology that's been used on things like FPSOs, where you have a lot of dead weight of chain. So the chain comes straight down first off before running along the seabed to a point where by the time you get to any anchor, effectively there's no load seen really in the anchor, because it's all taken up in the weight of the catenary. This system is not very stiff laterally, so it's probably of limited use on an SFTB. At the other end of the scale is a completely taut mooring system, where you have synthetic lines such as Dyneema here, and they run sort of point to point, and these are the ones that say can be used with the suction bucket technology quite effectively, so you can deal with that uplift load that is seen right at the seabed. And then between the two, there's a sort of halfway house, which is a semi-taut mooring system, which uses a combination of could use a combination of chain with synthetic rope, or it could use steel wire rope as well included in it, and that gives you a reasonably laterally stiff system, but with less overall weight than you'd see in a catenary system. So then we get on, we've built our units, and we need to transport them to site. You could be building quite a long way away from your final deployment site. It depends on where it's convenient to construct each unit. So you need a usual array of tugs to do that, and you have to plan that in relation to the length of the unit, what sort of sea states it can withstand when it's just a single unit on its own, being towed near the surface. It can be a consideration for design that the temporary condition can influence the design of the unit. And then I mentioned previously the alternative of deployment method using these immersed tube tunnel units, which comprise barges and a winch system. And I would say to use this system, you need a reasonably calm conditions. It's not for an exposed site, because the difficulties designing this temporary system and designing a winch system that can deal with the dynamic loads. But if you've got reasonably sheltered conditions, then it just could be considered. Of course, we've got to join the units together, and there was a question before lunch on what you do at the joints in terms of keeping the water out. But essentially, you're creating a full strength connection between the modular sections, and the way that's shown here is that you have some guide devices, so you can bring the units together and have a seal between them. You've got these end temporary diaphragms on the unit. You can then evacuate the water between the units, and then here we're showing introducing a post-tensioning connection to the units and grout between the faces of the unit, so that by the time you've grouted it, it's gained strength. You've applied the pre-stressing across the joint. Effectively, this section here should be as strong as any other section within the SFTBs. And how do you bring them together? Well, you've pre-laid your mooring system, and you may do this inshore, or you may do it at your final site. But you need to be able to pull each unit onto the assembled section of the SFTB. So this is going to need things like support barges and winches to pull the units into position, so that you can then hold it in position while you're doing that temporary work that I showed on the previous slide. Other arrangements have been considered, and this again is a study for Sognefjorden, where an inshore assembly location was considered to build or to assemble the whole length of the SFTB. And what was proposed on this one was that it's a bit of a sketchy sketch, but a cofferdam arrangement that you place around each joint, which is a sealed structure which you can then work inside and do a more conventional jointing operation, where you're putting rebar and concrete infill between each section before putting in that continuity post-tensioning. So how can you install the pontoons? Well, if you imagine this system here, it can be stable with the pontoons at this level here, but the system would not be stable if the pontoon was elevated to the top of the unit. You wouldn't get overall floating stability if you pre-installed your pontoons and they were elevated to a high level. So one means of using the pontoons to both install your SFTB and to connect up the pontoons is you can use some sort of jacking system where you can lower the SFTB down at the same time as holding the draft of the pontoon, and then making a permanent connection between what may be a steel frame that links between the two units. And looking at the tether technology that can be adopted, this is a typical tether arrangement. As I mentioned, these are hollow tubes. This one here is just over 1 meter diameter, and there are proprietary systems which are available from companies such as Oil States, which create connections at the top and connections at the bottom, which are sort of plug and play type solutions. So you can engage them in a previously installed unit and then lock them into position. And these are connector units between individual pieces of tube. So one method of assembling your tethers together is, if the tethers are not too long and you can construct somewhere relatively close to the site, then you can construct the length of string on shore, as is shown here, and then you can just pull them out and tow them horizontally before upending in the water. And this are some pictures from the Hedron TLP tethers, which was done in this manner. The alternative method uses the connectors, and I'll just show you a piece of, I won't show you the whole of this video, means of installing the tether. I previously showed putting a pile at the bottom and having a connector to it, and then you can bring along your lengths of tether. And then using a floating vessel, you lift up each piece of tether. And then the tether is hung from the side of the vessel, so it's clamped temporarily. You then fit one of those connectors to it. Bring along the next one. Connect it up. And then obviously you repeat this process, gradually suspending a longer and longer length of tether. And then finally, you connect up both ends. So you usually put temporary buoyancy on the top of a tether. And here we have the convenience of bringing in a tension leg platform, which is self-floating and surface piercing. The challenge with SFTBs is that it doesn't have any surface buoyancy, and you can't actually work from your unit when you're tensioning it up. So there are some challenges in terms of how you actually connect the tethers. So with our SFTB, we have to lower it down using whatever means we've decided, and we've got our pre-installed tethers. And the suggestion here is that you can have these tethers held back, so that you bring the SFTB into position, and then you can bring them in to sit in what we usually call porches here, to take the top end of the tether, and then you can make adjustments in this top end to get the right level of tension in the system, and the right elevation for this this level here. And that brings me to the conclusion.